ಎಲ್ಲರಿಗೂ ನಮಸ್ಕಾರ. ನಾನು ಡಾಕ್ಟರ್ ಶಿವಪ್ರಸಾದ್ ಎನ್.ಜಿ. ಭೌತಶಾಸ್ತ್ರ ಸಹಾಯಕ ಪ್ರಾಧ್ಯಾಪಕನಾಗಿ ಕಾರ್ಯನಿರ್ವಹಿಸುತ್ತಿರುತ್ತೇನೆ. ಈ ದಿನದ ತರಗತಿಯಲ್ಲಿ ಭೌತಶಾಸ್ತ್ರ BSc ಭೌತಶಾಸ್ತ್ರ ವಿಷಯದ ನಾನೋ ಮೆಟೀರಿಯಲ್ಸ್ ಎಂಬ ಒಂದು ಪತ್ರಿಕೆಯ ಕೆಲವೊಂದು ವಿಷಯಗಳನ್ನು ನಾವು ಡಿಸ್ಕಸ್ ಮಾಡಬಹುದು. The main topics for this class are length scales in physics, introduction to nanostructures, and one-dimensional, two-dimensional, and three-dimensional nanostructures. Now, let us see the length scales in physics. You know what is a scale? Scale, it is used to measure the dimensions of the object. So, in the physics students will be knowing very well. When we come to this nanotechnology, it is a new topic. It is the process of minimizing from micrometer scale, that is 10 to the power of minus 6, to nanometer scale, which is 10 to the power of minus 9 meters. Now we can say that 1 nanometer, we can imagine how a nanometer is. So 1 nanometer is equivalent to 5 silicon atoms or 10 hydrogen atoms placed in a line. Just imagine the atomic level, how big or how small one atom is. So that 5 silicon atoms or 10 hydrogen atoms, when we place in a row, in a line, that dimension is in the order of 10 to the power of minus 9 meter. Now, what are the changes that we can observe when we go from bulk to micro scale and micro to nano scale? When the size goes down from micrometer scale or a bulk material to the micrometer scale, no physical properties will be changed. So the physical properties of materials remain same. But when we take the material to the nano scale, there are drastic changes in the physical properties of the materials. For example, we can say that when we take the material from micro scale to macro scale, suppose gold, if we take from bulk size to the nano scale, the color of the gold itself changes. Whatever the golden brown we observe in the bulk, it will become changes. It will take another color when it goes to the nano scale. Similarly, there are many other physical properties. Their melting point may change, boiling point may change. Like that, many properties are going to change drastically when the material is taken to the nano scale. This is what the figure which shows the bulk materials, which is initially the bulk materials when they go for micro world, which is of 10 to the power of minus 6 meter, and the nano scale, which is 10 to the power of minus 9 meter, where the physical properties of the materials are going to change drastically. Now let us imagine the length scale. See, we have written different dimensions of scales here, 10 power minus 1, minus 2, minus 3, like that, from 1 meter towards the 10 to the power of minus 10 or minus 15 meters. We can show it here. Now let us keep on comparing the sizes. Now this is a human size. The human size is of the order of 1.75 meter, which is very visible to our naked eye. That is the size of the human. Next, a bit lower, size of the fly. The size of the fly is of the order of 10 power minus 1 to minus 2 meter. Now just keep on imagining the dimensions. Next, hair diameter. We know our hairs. So the hair diameter is of the order of 10 to the power of minus 4 meter. See, which is also visible to our eye. Now the actual invisibility starts, like RBC. RBC means the size of the RBC is of 10 to the power of minus 5 to minus 6 meter, which is in micro scale. Therefore, we need an external aid called a microscope to see the objects of these dimensions, 10 power minus 6 dimensions. Hence, these are all not visible to the naked eye. Next, virus size. It is of the order of 10 to the power of minus 7 to minus 8 meter. Similarly, the DNA size 10 power minus 8 to minus 9 meter. Now the nano begins. Then carbon nano tubes of 10 to the power of minus 9 meter. Similarly, size of the hydrogen atom, it is less than 10 to the power of minus 10 meter. So the single atom of the hydrogen is less than 10 to the power of minus 10 meter. So this is how we can compare the sizes from the bulk to nano or bulk to angstrom sizes. Now, when we come to the structures, nanostructures, they are the intermediate size between microscopic and molecular structure. So, molecular structure and microscopic structure ಮಧ್ಯೆ ಬರುತ್ತೆ ಈ ನ್ಯಾನೋ ಸ್ಟ್ರಕ್ಚರ್ ಅಂತ ನಾವೇನು ಕರಿತೀವಿ ಅದನ್ನು. So, the nanostructures size are within few nanometers. It is less than 100 nanometer and can comprise of either single material or multiple material. These nanostructures with multiple material can again either be a simple like polymer metal nanocomposite or silica metallic nanoparticles or graphene gold nanoparticles and so on, or in the form of core shells. Like this the nanostructures begins. See some examples we have shown here. Silicon nanostructures are having this shape, and carbon nanostructures, these are the carbon nanostructures, and this is the steel nanostructures. You can see the different colors which are exhibited by the materials when they go to the nanoscale. Now, let us see dimensional nanostructures like one-dimensional, two-dimensional and three-dimensional nanostructures. So, when we come to one-dimensional nanostructure, these are the materials having one dimension whose one dimension is outside the nanoscale and remaining two dimensions are within the nanoscale. Examples: nanowires, nanorods, nanotubes, nanopillars and carbon nanotubes. So, these are the one dimension is grown and other two dimensions are in the nanoscale. Such materials are called one dimensional nanostructures. So, it is like just imagine our wires, rods, tubes, lengthwise they are more, but the other dimensions, other two dimensions, they are in a nanoscale. Next, two-dimensional nanostructure. Two-dimensional nanostructures are the materials having two dimensions are outside the nanoscale and remaining one dimensions are within the nanoscale. So, it is like a graphene, film, nanolayers, carbon nano coatings. It is like a flat coatings, films. So, these films are two dimensions are outside the nanoscale and one dimensions are within the nanoscale. Such structures are called two-dimensional nanostructures. Similarly, three-dimensional nanostructures. These three-dimensional nanostructures are not confined to nanoscale in any dimension. All the three dimensions are larger than 100 nanometers. So, in X, Y, Z, all the three directions, the material size is greater than the nanoscale, that is 100 nanometer. Example we can give: graphite, diamond, bulk powders, dispersion of nanoparticles, bundles of nanowires. These are all the examples for three-dimensional nanostructures. Now we can see the pictorial representation. See nanotubes, they are like tubes, long tubes. So they are one dimension. Next, graphene. See, it is a layer, a plane layer. It is a two-dimensional. See, these are the three-dimensional. Graphite and diamond are the examples for three-dimensional. All three directions are grown up. So these are the pictorial representation for one-dimensional, two-dimensional and three-dimensional nanostructures. Next, let us see how the band structure of nanomaterials is. Basically, nanomaterials are the materials having the size range in 1 to 100 nanometer that we know, and band gap is the energy gap between the valence band and conduction band. That is by definition. Band gap is the energy gap between valence and conduction band. Let us consider an example of silicon atom whose configuration is 1s2, 2s2, 2p6, 3s2, 3p2. Now neglecting the influence of the inner shell levels, 2n s electrons will fill all the 2n possible s levels, and 2n p electrons will fill 1/3 of the possible 6n p states. This p state, 6 atoms, it has a vacancy for 6 electrons. Now, the discrete energy levels are formed. When we bring the atoms close to each other, the 2n s states and 6n p states will spread into respective 2n and 6n discrete levels. So, these states will spread into the 6n discrete level. The n value is of the order of 10 to the power of 23 centimeter cube, and the separation between the discrete levels will be very small, and therefore these closely spaced energy levels are treated as quasi-continuous state called energy bands. So this is the energy band structure for the nanomaterials. Symbolically, it is shown the splitting up of energy levels for isolated atoms to energy bands due to coupling between the atoms. So when two atoms are coupled, see this is the 6n, actually this is the energy gap between the valence band and the conduction band. This is the energy difference. So 6n and 2np electrons are here. So 2n degenerate states is this, and the atoms are present like this. Similarly, the band structure for nanomaterials, this is the formation of valence and conduction band at a lattice spacing. Now, how the valence and conduction bands are formed in the lattice spacing, which is again 6n degenerate states, 2np electrons. Similarly, this is 6n non-degenerate state, which is 2np electrons. This is the energy gap where 2n non-degenerate states and the 2ns electrons are present. Now, this is an isolated atom which is in 2n degenerate states and 2ns electrons. This is inner shell energy level gap, what we see here. So this is how the band structure of these nanomaterials are formed. Thank you for watching this session. I hope with this discussion we I'll recap what are the things that we learnt about this session. So different length scales in physics we seen. What is bulk state, what is micro state, and what is nano state, and in nano state what will be the dimensions and all we came to know. After that, nanostructures we came to know. In the nanostructure, one-dimensional, two-dimensional and three-dimensional nanostructures we understood. After that, band structure of the nanomaterials we have seen. So the band structure also completely understood with an example of silicon atom. Thank you so much.